In this video, I'm going to describe what these are and why I needed to design them. Then I'll go through a demonstration of how they work and go through several scenarios. And then finally, I'll go through the circuit diagram and describe how the circuit is constructed. So on the left-hand side of these, you can see there's a 2.7 volt, 500 farad super capacitor. So that's really the basis of this. Is I need a way of releasing power in a very quick fashion. So these supercapacitors, they can not only accumulate power very fast, but they can release it very fast as well. And in order to charge them up and make use of the power that's been charged in them, I need a circuit to do that, because if you just connect the power source across the terminals of a supercapacitor, it's like shorting out the power source. So I needed a controlled way of actually charging up the power source. So I'm going to start off with this one on the left. In fact, I'll put the one on the right to the side for now. And this one, I've actually discharged the supercapacitor pretty much fully. Well, I discharged it fully, but there's always seems to be a slight amount of charge in them. So if I look at the voltage, there's about 230 millivolts in that supercapacitor. Now on the back I've got an 18650 battery holder, so I've got a double battery holder. So I'm going to connect two 18650 batteries in parallel. Now when connecting 18650 or lithium ion batteries in particular in parallel, it's very important for them to be at the same charge as each other, because they release energy themselves so quickly. If one of them's half charged and the other one's full charged, then it will transfer power from one battery to the other very rapidly, and there's a risk of fire. So it's important to just check the voltages of the batteries. So this one is at 403, 4 volts and 3. So I've charged these fully, and this one is at 403 as well. So it should be safe to put these into this device. Now I've got a 10 amp fuse here just to protect the circuit. I'm going to lift that fuse up and use it as a kind of a switch. But what I'm also going to do is I'm going to demonstrate. So from no charge at all, it will actually consume a lot of current when it's empty, and then it will consume less current as it charges up. So I just wanted to empty this one out so I could demonstrate exactly how much current is transferred on the fully discharged capacitor. Supercapacitors tend to maintain a certain charge, so it's very rare that I think it'll be charging up from absolute empty. Now the other thing to be careful about these 18650s is that they go around the right way. So there's positive at the top, negative down the bottom, and putting them in reverse order is a really nasty thing to do. So I'm gonna put that one in there. Make sure I don't close the circuit yet, and make sure I get this one the right way around as well. And that would be nasty as well, putting one cell in one way around and the other cell in the other way around. So if I put that here, now what I can do is I can change my meter to the 10 amp setting and move the plug across to the 10 amp plug. This is just to show how much current these consume from empty with this circuit. So I'm going to use the current, the ammeter in the input over sort of between where the fuse would normally conduct, and see how much it takes in. So that's taking, that was almost 9 amps, and that's dropping down to 8 amps, 7 amps, and so on. So it consumes a lot from empty. Now what I'll do is I'll close this fuse and let it charge up by itself. And the average kind of consumption is about 5 amps. And when it gets up to about 2.2 volts, I've got like a PIC microcontroller in here, and it displays the voltage on the display up there. But this heatsink gets quite hot, because it's only a small heatsink considering the amount of power it's transferring to the supercapacitor. let's just if I make sure that I change this back to volts so that I don't short out batteries or anything. So if I look at how that's charging, so that's 1.69, 1.7 volts at the minute. When it gets up to 2 volts, or around 2, maybe a little bit over 2 volts, then the display should come on and start displaying the actual voltage there. But whilst that's doing that, this other one I've left for a few hours, and this is the kind of voltage that the super capacitor normally gets to. Just make sure that I'm still on volts. So if I measure the voltage across this one, so about 1.9 volts. It normally settles down to about 1.5 volts, something like that. But that's currently at 1.9 volts. So I was going to charge this one up as well. So there that one comes up, and it's at 2.24 volts, and it will display. And so there's 4 volts across those batteries, but because it's taking so much current, it's got about half a volt drop over what the full batteries were, and then that will just charge up. It takes a few minutes to charge up from empty up to 2.7 volts, but this is charging quite rapidly. I mean, that's probably charging about 5 amps at this point in the charge cycle. And this is a little feature on the side here, this little yellow LED. When the voltage gets up to 2.5 volts, I light that LED up so that it tells me that actually there's enough current in the capacitor that I could actually that's useful at this point, so I could use it now. And then when that little LED goes out, I know that actually I should just pause for a while and let it recharge a bit, and then use it when it gets up to charge. So that's now up to 2.7 volts. I was actually going to charge this one up, but actually there's no point in doing that because I wasn't sure that it would charge up quick enough, sort of whilst speaking over it. Now you see that there's a few millivolts of noise. So when it was charging up, it was nice and steady. Now it's just doing the last few millivolts of charge, and it gets a bit noisy at that point. I think it's the MOSFET switching. I haven't looked into actually cleaning that up yet, but it's basically at 2.7 volts. So I've made 4 of these circuits. So I've got I'll just move the voltmeter out of the way. So I've made 2 of these up because I've got 2 super capacitors now, and I've made up a couple extra boards which I'll put on the big super capacitors, and I've just been testing them with a small 10 farad super capacitor. And what I'll do ultimately is connect them in series, the capacitors in series, so actually they can charge up whilst they're connected in series, because the batteries are independent of each other. So the batteries will charge each element up, and I'll have the capacitors in series, which will give me about 10 volts. And I'll be able to use that 10 volts for quick bursts of high current, which I'll use to weld these little nickel strips to 18650 cells. So I want to make up battery packs, and these are usually welded to the 18650 cells, usually sort of on the backs like that, and then they're all done in series or in parallel depending on the requirement. Because it's a bad idea to solder these onto 18650 cells, because lithium cells, if they get too hot, then they could explode. So if you're trying to solder stuff onto a cell, you can get like a really hot spot where you're soldering, and there's a risk of causing an issue with maybe an explosion with the battery. But with spot welding, which this setup is hopefully going to do, it's like a very localized high temperature, very just where the spot where you're welding. So actually it doesn't affect the internal chemistry of the battery, and hopefully it should be nice and safe to do. And then I can make up a big battery pack. So before I actually get to the circuit diagram itself, I'll just take the display off of this one and just go over. It's a very basic circuit. There's quad op amps here, and the op amps are used to control the voltage on the output of the MOSFET to make sure it doesn't go above 2.7 volts. And there's like a little bit of a boosting circuit down here as well. So that's the main. This bit of the circuit here is what does most of the features, including like the yellow LED when it gets up to 2.5 volts. Then this PIC microcontroller, all that does is it controls the display. It reads the voltage from the battery and the capacitor side, and it will just display it. But the circuit will actually work without this microcontroller, without this display. So actually this bottom part of the circuit is pretty much what the circuit is. So this is the circuit diagram for the device. And I'll break it down to smaller bits. So this is the overall thing, and there's a few functions within this. I'll break it down and I'll go over this bottom section around here first. And then I'll cover this bottom left-hand corner, following by these op amps in the middle here. And then last of all, I'll describe the microcontroller and display at the end. So this part is a basic power supply. So there's a 10 amp fuse here. I've got 10 amp fuse because it takes up to 8 amps of current when the supercapacitor is empty. And if the MOSFET blows, which is here, then it will fail short circuit, and it will just dump a load of amps into the battery and into the supercapacitor. Sorry, and so you've got 10 amp fuse just to protect it from dumping too much. And then there's a couple of op amps. Now this one here, there's a variable resistor here which is set to the voltage you want to actually charge the supercapacitor to 2.7 volts. And so the output of that op amp goes into the MOSFET. Now you actually need 10 volts to actually charge that, to actually switch that MOSFET on. So I'll describe in the next part how I generate 10 volts to actually switch that on. But the actual op amps here, it's like a quad pack. There's two more which I'll describe later on. The actual power to that op amp integrated circuit is the 10 volts which I want to actually switch this on by. So when this op amp is switched on, it swings to its high voltage. There's actually 10 volts that comes out of here because the supply to the op amps is 10 volts. But the input to the op amps doesn't have to be 10 volts, so you've got 2.7 volts. And this 100k resistor here is feedback, which is here from the output. So the output of the MOSFET feeds back into the op amp, and it makes sure that the voltage is constrained to 2.7 volts. So if it's greater than 2.7 volts, it switches the MOSFET off, and if it's lower than 2.7 volts, then it switches the MOSFET on, and thus it generates at 2.7 volts at the output. And it will just end at that voltage that it's trying to put out. It will just put as much current as it can without going over the 2.7 volts. So this is just like a standard power supply kind of concept. So that describes what this op amp is for. It's for controlling the MOSFET and making sure that there's 2.7 volts on the output. But this other op amp, it does a similar kind of thing because it does a comparison of a voltage, but this time against 2.5 volts. Because what it wants to do is it wants to turn this MOSFET on, and when that MOSFET is turned on, this yellow charge light goes on. So anything below 2.5 volts and the yellow LED is off. Anything above 2.5 volts and the LED comes on, which is my indicator to show me when it's safe to use the power from in the charge stored in the super capacitor. And you'll notice that this 2.7 volts is on the V minus input because I want to switch on the op amp and the MOSFET when the voltage is below 2.7 volts. But this one is on the plus input because I want to switch on the LED when the output voltage goes above the 2.5 volts. So they just switch on in opposite cases. But they basically do very similar jobs because they both take the feedback from the output, so they can decide on the output what to do. So this next part of the circuit, you can see the 10 amp fuse from previous description. It's just got a little power LED so that when the power's on, it just shows a green LED to show that there's power present. But this is the main part of this part of the description, is this here. It's kind of a power supply. So you've got a basic dual thief type circuit, and I'm just using a dual thief circuit with 5 to 20 winding on, so 5 windings on that side, 20 windings on that side, and it just generates it boosts the input voltage of where it can be 4 volts or it can be as low as 3.5 volts, so anything between 3.5 to 4 volts input. What I want to do is create 10 volts output, so I've got a Zener diode here to restrict the output to 10 volts. So this just boosts up lots of boosts the input voltage, stores it in this capacitor here, and then the Zener diode restricts what's stored in this capacitor to be just 10 volts. And then I use that. So it doesn't actually generate much current, so it doesn't have much driving capability what's in this capacitor here that was stored in there. But I need it for a couple of purposes. So one is this 3.3 volt regulator. I use this to have as a reference for specific voltages. So when I set the 2.7 volts, I use this regulator here to give me a very specific constant voltage, which I can set my 2.7 volts to. I can set the 2.5 volts to, which was in the last description. And also I need it for my microcontroller so that I can set a voltage for the ATD converter, which is a very specific voltage to actually read the voltages from the circuit itself. So that's basically what this area does here. It just provides me with a few voltages which are relative to this 3.3 volts for accuracy. So in this next section, so down the bottom here, I've basically described this before, but just as a reference, so this is the 10 volts coming out of the the boost converter. It gets regulated down to 3 volts 3 from this regulator here, and then into this op amp I have a potential divider, and that generates the 2.5 volts, and similar I have a potential divider here which generates the 2.7 volts that I need, and these potential dividers are adjustable, so I can actually change the voltage if I wanted the yellow LED to come on at a different voltage, and to make sure that I've got, rather than just rely on the tolerances of resistances to give resistors to give me 2.7 volts, if I make it a pot, then I can make sure that I've got the exact 2.7 volts on the output that I need. And then here's the other two op amps up at the top, and these are configured slightly different to the op amps down the bottom. So these op amps are basically amplifiers, but these are at the top are configured as voltage followers. So actually whatever voltage goes into the plus side is the voltage which comes out of the output, and that's done so that I can feed whatever comes out of these into the microcontroller, and and it gives a decent amount of current for the ATD converter to do its conversion and read what voltages are going into it. But I've got potential dividers here also going into here, so when I read voltages from the circuit, I can I can calibrate them so that the microcontroller, what it reads and displays is actually an accurate voltage of what it's reading from the circuit. So one of the voltages is this feedback here, which is the 2.7 volt output. So I'm reading the output voltage, and then the other voltage is coming off of here, which is the capacitor voltage. So I'm reading the voltage of the capacitor and the voltage of the output, and then the signals just go off and into the microcontroller, which I'll describe next. So this top bit of the circuit is not really necessary for the driving of the circuit. It's just there to display the voltages. So what's really necessary is this bit of the circuit here and backwards. So this part of the circuit is not really much to it. It's just a microcontroller and a display so that it can display the voltages which it reads from the circuit. The only other part really is this bit here. It takes the 3 volt 3 coming in from here, from the regulator, and it uses a potential divider here to divide it in two. because it's using that as a reference for the A to D converter. So this actual microcontroller is actually powered from the super capacitor, so it's at about maximum of 2.7 volts. But as the super capacitor can vary in its charge from say 2.2 volts when this microcontroller will be switched on to 2.7 volts, then reading the A to D converter isn't very consistent, because the supply, if you use the supply of the microcontroller as a reference for the A to D, as the supply of the microcontroller is varying, the reading of the voltage will be all over the place as the charge in the capacitor changes. So on this pin here, I can have a VREF input, and so I have 1.65 volts as my reference. VREF has to be less than the supply pin of the microcontroller, which is why I've had to divide the 3.3 volts down by 2 to put it into the microcontroller. And then my controller has a switch, so I can do various functions if required. So to finish off, this is just an overview of the whole circuit again, with the boost control converter here providing all the different voltages I require for the circuit, and there's quite a few different voltages at different stages. So they're all, and this sets some configures voltages for the voltage readings. Yep. So this is the power supply part. This is the voltage reading part and the voltage display part.